Hey guys, today we're going to get into bond polarity and molecular polarity. Starting things off, we want to go ahead and take a look here at the way that covalent bonds are really structured, what's happening when two atoms come together. First thing that you'll notice is different atoms have a different electronegativity value. That's a different pull on electrons, right? So if I have two atoms that are different, one of them is going to pull more than another. If I have two atoms that are identical, then they're going to pull exactly the same amount. So we think about diatomic molecules, for example. Here I have hydrogen atom with another hydrogen atom, right? So this is a three-dimensional structure. We can also picture it as a Lewis structure, right? So this covalent bond that we're looking at, the electrons pair, that those two electrons are shared in this space between the two hydrogen nuclei. Well, if it's hydrogen with hydrogen, then there's no difference in their ability to pull on those electrons. So what you would see is that there is an exactly perfectly equal pull from the two nuclei on those electrons in the bond. When that happens, we describe this as a non-polar covalent bond. Okay? No difference of electronegativity. Again, the idea here is that the electrons are shared and they are shared equally, exactly, perfectly equally, meaning that the electrons are dead center most of the time. If there's any shifting that occurs, it shifts slightly to one side or slightly to the other. The amount of time it spends on either side tends to be even. Okay, so exactly even equal sharing. We also have to think about what happens when you don't have equal sharing. Okay, if you have two atoms that are bound together in a covalent bond and they're different atoms, they have a different nuclear structure, they have a different ability to hold on to electrons. So keeping that in mind, we would look at a structure like hydrogen with chlorine. The bond between hydrogen and chlorine is not equal. Chlorine is more electronegative. So that means that it is going to pull electrons closer to the chlorine compared to the hydrogen. We call this a polar covalent bond. Now, when we have a bond that is polar, we have to have a way of indicating that difference of electronegativity because it's going to reflect the way that this thing behaves outside the molecule. The way that we can do this is with something called a bond dipole. Now, a bond dipole gives a couple of specific pieces of information. The bond dipole will tell us the direction of the more electronegative atom. So where is that electronegative side of the bond? And it also tells us the magnitude of the bond. So if we look here, we have hydrogen atom and we have iodide atom. The hydrogen is going to have a relatively low electronegativity. Iodine is going to be higher. So we draw a bond dipole. It's an arrow. Notice that that arrow has kind of a cross on the tail, and that is to indicate that this is the positive side of that, the bond. The positive side is towards hydrogen. The negative side is going to be up here towards, oh, we gotta love when that happens, up here towards our iodine. So the bond dipole really is just an arrow that points in the direction of the more electronegative species, and it has a cross as a tail indicating the more positive species. Remember that direction is one important aspect here, but the other thing is magnitude. If you have a very, very big electronegativity difference, you would show that with a larger arrow. So if I have hydrogen attached to fluorine compared to hydrogen attached to fluorine, well, fluorine is the most electronegative atom that we have. So if hydrogen chloride is shown with a bond dipole pointing to the chlorine, the length of the hydrogen fluoride bond dipole is going to be greater. It's going to be longer to indicate that that's a bigger difference of electronegativity. And it means the electrons shift closer to fluorine when we have a bond between the two. Next idea here is that of electron density. Now, density is how much stuff is in how much space, right? So the atom that has a higher electronegativity draws electrons closer in the bond. So we would say that it has a a greater amount of negative things surrounding it. It has a larger negative charge, but it didn't completely take those electrons away, so we wouldn't say that it's a negative ion. We would say that it is an atom with a partial negative charge. So looking again at our hydrogen and our fluorine example here, well, fluorine is much more electronegative than the hydrogen. So we show that with a more shaded region, it's got a higher density of electrons on that side compared to the hydrogen, which is less shaded, meaning that there's a lower density of electrons present there. Now, this representation in a quantifiable form, we can actually see the difference of electronegativity represented by a lowercase delta symbol. That means partial charge. The fluorine has a negative partial charge of 0.43 in this bond, and the hydrogen has a positive 0.43. So again, notice that when this pairing occurs, there's going to be a balance of charge. If you were to combine this, you see that the net charge of the bond is still 0. Now, we had talked about nonpolar bonds, but now we want to extend this slightly more into molecules. So we're going to talk about 3-atom molecules now. Looking down at our graph, notice that we have atom A, B, and C. Well, we talked about binary molecules that would just be an A and a B. They can be nonpolar when you have 2 identical species. In this case, we can have a nonpolar molecule based upon a couple of conditions. The first thing is that the dipoles that do exist, the dipoles must be equal strength. They have to be in exactly the same strength. So that could be something like carbon paired to oxygen and oxygen, right, in these bonds. Well, carbon has a dipole pointing out towards oxygen, the more negative species, and it also has a dipole pointing from carbon out to the right-hand oxygen. Well, carbon to oxygen and carbon to oxygen, that's the exact same difference of electronegativity, so it's the same magnitude, it's the same strength of a bond dipole. The second factor that we have to have here, though, is that these dipoles must be in canceling directions. So if you have a molecule that is linear, it's in a straight line like you see here, notice that with our A, B, and C, the bond dipoles are pointing inwards towards B, which we show as a more electronegative atom. In this case, though, because they're perfectly opposite, they're pointing straight towards each other, they're in canceling directions. With our carbon dioxide example, both of them are pointing out, but in perfectly opposite directions. So as long as they're in a canceling direction, we can have a nonpolar molecule. The overall shifting of electrons cancels out based upon those bonds and the direction and the angles that we're looking at. So we're going to spend more time looking at bond angles and how this works, but we're going to have to start thinking of 3D geometric shapes when these molecules are forming, because we know that we can have bonds that have more than 3 atoms in them. A polar molecule, one really big important thing, remember how we talked about bond dipoles? We care about these bond dipoles because they give us insight into the way that these atoms and molecules react to things outside them. Well, we find that polar molecules are affected by electrical fields. If I have this molecule, notice we have oxygen, hydrogen, and hydrogen. Notice at this time, it's not a linear structure, it's bent. So that means that my bond dipoles, as I'm pointing up to oxygen and up to oxygen, these aren't in a canceling direction. They're both pointed slightly upwards. So they cancel going in, but they stack up going upwards. So this gold arrow that we've drawn here, we call that a molecular dipole. It's the combination of all of the bond dipoles that we would see. Now, remember that we have evidence of polar molecules because they're affected by electrical fields. So if I introduce a negative field here on the left and a positive on the right, when I turn on that field, you'll notice that the molecule itself will shift. It's going to rotate so that the more positive side is attracted to the negative field. That's this partial positive. And then the more negative side, that's where our gold arrow points out, that partial negative charge is attracted to a positive field. This is again one of the reasons why you have polar molecules that can dissolve in water, which is a polar substance. The water has the ability to rearrange the positioning of these substances and rip them apart from their attractive forces. So this happens with ions and also other polar molecules. Now, you have a couple of practice problems here. We'll start with this one. The molecule below has no bond dipole. Take a minute to respond to that, think it through, and try to justify, do we know does it have a bond dipole or no? Second question, the molecule below has no bond dipole. Question 3, our molecule below is polar. This is oxygen with 2 hydrogens. Question 4, this molecule contains bond dipoles and has a molecular dipole. So if both of those concepts are true, mark true. This molecule contains both bond dipoles and has a molecular dipole. So again, if both of these ideas are true, mark true. This molecule contains bond dipoles and has a molecular dipole. In this case, again, if both concepts are true, mark true. Next, this molecule contains bond dipoles but has no molecular dipole. This is a true statement, mark true. Question 8, this molecule contains bond dipoles but has no molecular dipole. If this is a true statement, mark true.